What? Okay, write this down, please. Okay, continue. Right, so a capacitor is fully charged up, like in a flash camera. And then what you do is you allow it to discharge, meaning you let the charge come out through some resistor. For the camera, what would the resistor be, do you think? So you have the capacitor is charged up, and then the charge comes out into a resistor. What is offering the resistance? What's the resistor here for the camera? Huh? No. How much electricity passes through the lens, do you think? Exactly. So try again. Possibly the light bulb that's flashing? Yes. Yeah, it's a good idea, isn't it? Yeah. So, like the light bulb. So I won't draw that because it's not necessary. But notice how this, well, you know, actually I do need to, sorry. So what we have here is a battery, a cell. Well, let's make it a battery. And then a capacitor, a switch, and then here a light bulb. So at the beginning the switch is, oh no, that's not quite right, sorry, I need to fix my switch here. Let me just think. Oh, sorry, my switch is over at the corner here. So at the beginning the switch is like this. Yeah, so the charge moves along here, and what happens to the capacitor? It charges up. Got that? And then you click, and this moves down into this position. Yeah, so now all the charge that was here is released into the light. Like this. Okay? What we want to look at today is we want to know how does the voltage change around the resistor. So you could probably imagine at the beginning it's very high and then it decreases as this loses charge. Notice how we have one resistor and one capacitor, essentially. So that's why we call it an RC circuit, a resistor and a capacitor circuit. Let's put in an ammeter as well, instead of a voltmeter first. Here's an example of what the numbers might look like. At the very beginning, you got 100 milliamps. But can you see? Well, okay, this isn't for a camera because the time is not 10 seconds. And for whatever it is, as the time gets bigger, what happens to the current? It loses, it decreases, because the capacitor is, what's the word? Discharging, losing charge. You see that? Yep. So, as you can see, the graph is exponentially decreasing, because what I'll do now is I'll make this graph, and I would like you to make this graph. So what will we put on the X and what will we put on the Y?
Curve is
Current is on the and time is on the X. Let's draw that. can you just copy that table down first as an example? Got that table? Okay, let's make the graph. Okay. So, no surprise that the graph, we should expect to see it going down. Okay. Where'd you get all that blue tack from? No, where'd you get it? Why'd you buy blue tack?
We all have to.
You had to buy blue tack. Alright. Time. Time in seconds. Time in seconds. Current in milliamps. Can you tell me please the time? It starts at 0, doesn't it? 0 to 10. Okay. And then what is the milliamps doing? What's the first one? 100. And the next one? 70.7. Oh, you say that, but I'm convinced there is. 70.7, yeah. 2 decimal places or 1? 1 decimal place. For everything or for some of them? Okay. I'll just do. Oh, I see. No. Is the next one 50?
Yeah.
Don't worry, I believe in me. Now, let's make the graph here. What's wrong, Flan? Are you writing this down? Yeah. What type of plot do I need here? We'll go with scatter and we'll connect them up. And we'll call this current against time. Time, seconds, and axis is current in milliamps. So we get this shape. Okay, one day we'll give you a graph, okay, but not today. Okay, have you seen these graphs in maths class with your maths teacher, Stephen?
But how to make the big side to be right?
What do you mean?
The like, for example, the current. How to make it not like that, like this?
Or the what to become?
The word.
Because the word is now.
Huh?
The word that is
The word current,
right.
yeah.
I want to.
No, this is better.
No,
Yes.
that's too hard.
No, this is better. Yep. Okay, so the shape is called exponential. Remember we did the exponential graphs? Yeah? Now, this is exponential. So, because it's exponential, you know the formulas from maths class. It's AE with a power. So that means this graph here must have been something like this. I equals I0, well, it was something like this. I equals A, E, K, or B, or whatever, B, T. This is the form of it, where A is positive and B is negative. So, usually we write it like this. I0, E, and instead of using the constant B, we use this constant 1 over tau. It's a Greek letter. Tau. Yeah. So this is the form of the graph. We can see what the I0 is. What's the I0 on this graph that I just drew? What's the current at the beginning? 100. But what we can't see is what is the B constant. But what about this? Well, before I continue, there are not many proofs on the exam. In fact, I think there's only 3 proofs maybe they ask. The first proof that they could ask for the exam is the proof of the UVATS formulas. It could be on the exam. The second proof they could ask you on the exam, there's 3 in total, is what I'm about to do now. So you want to write it down carefully. So please make a note. Let's look at this proof I'm about to do of a formula. Okay, are you ready to write this down carefully, please? If you have I equals I0, E minus 1 over tau t, and you plot that with t and I, you get a graph like this. Let's put a log on both sides. Log I, log this. Come on, write this down, Lee. Log I equals log I0 plus log E minus 1 over tau t. So that means log I equals log I0 minus 1 over tau t. That means log I equals minus 1 over tau t plus log I0. Now if we call this y, call this x, so we have a graph with t and log I, or in other words x and y, what shape will this graph be? Well, it's like this form, y equals mx plus c, so the shape will be linear. So in other words, if you change I to log I, you'll get a linear graph, where we'll continue in a moment. Okay, you got that? No. Continue? Yep. Okay. So, let me just go back here for a moment. Let me just put in, I don't want to lose these numbers. Can I insert column to the right? No, I mean insert column to the left. I might have to type it in. Equals, can you type in log and tell me what each one is? So if you type in log 100, what do I get? Did you type LOG?
What?
Did you type LOG?
Yeah.
LN?
log is base 10, log is base
I'm sure I said this in class, right? Yeah, thank you. 4.61. Okay. Next one. Now you see these are all going to disappear. Did you write these down? Yeah, okay. So what's the next one then? See, they've all changed. Wait, I know what I'll do. No, it's okay. I don't need you anymore. Insert columns left equals log the number here. Let me copy, cut, delete. I can do this. There we go. So if instead I plot the log of the current instead of the current, you notice how now I have a straight line. Is that okay? So the point is, if I already did it. If I plot log I instead of I get a straight line graph now. Yeah? So in the exam, they sometimes trick students by giving them this and asking them to plot. But this is not the plot you should make. You should make a plot that has log I instead of I. So before you start, you need to calculate log I.
So they won't say what
Exactly. They will keep it unclear. They'll say, plot this in an appropriate manner. You know? Okay, continuing. So, if you have this formula, what happens when we put a log on both sides? I just showed you, you end up with this formula. Where you said, Yusuf, this is like M and this is like C. So, if y equals log I and x equals t, the slope is like 1 over tau, and the c is like log I 0, but you said that earlier. So, there's nothing new here, we talked about that earlier. So, what's nice is that this formula is true not just for I, but also for the charge. It decreases exponentially, so you get the same deal. And the voltage also decreases exponentially. So what's nice here is it's the same formula for all of them, except you just replace the I with a V or a Q or whatever you need. Yeah? We haven't talked about what the T represents. The tau. The tau has a special name. I don't know if anyone knows it, if they've done it before. It's called the time constant. And if 1 over tau equals the slope, then what will tau equal? Minus 1 over the slope. Like this. And there's a second formula for calculating tau. Tau actually equals the resistance in the resistor multiplied by the capacitance of the capacitor. Both formulas are very useful. Also note, so why do we care about the time constant? Well, the reason the time constant is important is because it tells us how long for it to discharge fully. So for it to completely discharge all of its charge, it will take 5 time constants. So obviously the unit for time constant is seconds. So if the time constant was 2, how long until it's fully discharged? 10 seconds. No surprise, the units are seconds. Okay, continue. Continue. 1. Right, I just have one example to do. Can the time goes from 0 to 100, so let me just put that in here. And what unit is the time? Be careful, milliseconds. So the time here is milliseconds, and it goes from 0 to 100. Okay, next I need the current. It's in milliamps. Right, so what's the first one? It's 1000. And then the next one is 841. And then the next one is 707. And the next one is 595. And the next one is 500. Oh, thank you. 420. 354. 297. 250, 210, and then 177. Graph this. Do I graph the I or the log I? Log I you should graph. Okay, so let's graph the log I. So I'll just need to calculate the logs now. So log of this thing. Let's calculate the logs. These are all the logs. Let me just delete that. Delete, escape, paste. And now it's not I, but instead it's log I. So we get this nice straight line graph. What does the slope represent here? Minus 1 over time constant. And what do I ask you for in part B? The time constant, which should be minus 1 over the slope. Let's calculate the slope. We shall use the formula you know from math class, which is y2 minus y1 over x2 minus x1. So we'll take this as y2. What's that? 7, we'll say? Minus 5. Now, in the exam, they want you to see pencils on your graph to show that you read the graph. You know, like draw a line across. And then the time is 100 minus 0. 1 over 50. But you have to be really careful. Just wait. I don't say the time constant is 1 over 50 because I need to work out the units. So it might be seconds, but it could be milliseconds because we're using milliseconds and milliamps. So let's double check here. This is equal to this. So the units for this will be equal to 1 over the units for the slope. What's on the y-axis? Log milliamps. And here milliseconds. So this will be milliseconds over log milliamps. So on the top, you remember it's like T2 minus T1 over log I2 minus log I1. What unit is T2 and T1? They were milliseconds, weren't they? What units were these? Log milliamps and log milliamps. So on the top we have milliseconds. But here we actually have no units. It's a bit weird, but it's log milliamps minus log milliamps, which is log milliamps over milliamps. Yeah, so actually the unit is milliseconds. In other words, the unit for the time constant is always the same unit as the time. That actually should say milliseconds. Can I change this? Anyways, it doesn't matter. We have it as 1 over 50 milliseconds. How long until it fully discharges? 5 of these, which is 5 over 50, which is 1 over 10 milliseconds. And what is the value of the resistor? Well, we can use this formula. Tau equals RC, so R equals tau over C. which is 1/50 milli. And the capacitor, I tell you it is in the question, it's 200 milli. So that's 200 times 10 to the minus 3. So you can work it out. You're confusing. You're a tired teacher. Thank you. 10 milliohms. Let's see again, show me. Yeah, she typed it in right. Anyways, this question is not very difficult. All you do is make the graph and then calculate the slope, and the slope gives you the time constant. Yeah, hang in there now. You've only got 10 seconds left and then we're finished. There's only one question for homework. I know, I'm too generous, but you know, it's my weakness. So, just one question to do for Monday.